So let's start looking into the dipole field. Now, the most simplest form or place wherein we can start off is axial point. The first thing is, what is this axial point? Say we have the charges and this is a line which is said to be the axis of the dipole. Now, any point on this is your axial point, as simple as that. So if this is Q and this is minus Q, so the electrical field between this space is what? Well, it's in this direction, is it not? Right, away from your Q towards minus Q. So before and after, or not within this space, right? Not within this space. What is the electrical field is what we are trying to learn. So after this or after this, however you guys want to think of it. So not between this space. What is the electrical field? What is the strength and direction, so on and so forth. That's what we're trying to learn. So the derivation will start like this. This is how you guys have to write in your exam. So let's consider a dipole with charge plus Q minus Q separated by a distance of 2a. Let P be a point on the axial line. At a distance of r. So if this is O center, this distance is r. Right, that's your entire figure. We can add few things. One is your dipole moment direction, and what else? That's it. I think that's good enough. Or we can do this also if you guys feel like it. That will be r minus a, and from here till here it will be r plus a. Remember, to the center it's a. From the center to point P, it is r. You can do the math. It's quite simple. Now, what is the net force over here? Well, the negative charge pulls while the positive charge pushes. So E positive Q is pushing and the electrical field over here is pulling. So what is the net force? Therefore, the net field at P is, sorry, just a second, E minus Q minus E plus Q. Or let me just write it. It is a vector sum of these two. Agree? This is as per superposition theorem. Now, when you open it up, how does this look like? Well, we have Q by 4 pi epsilon naught into 1 by r minus a the whole square. That's how far the negative charge is. Into, again, we're looking at vector representation, p cap. Because it's in the direction of p, can you see that? It's a pull. So it's in the direction of p itself. So it is positive. While this would be negative. Which one? The positive q, which is at the distance of r plus a the whole square, right? If you guys want, only for your reference, this is positive as E minus Q is in same direction as P cap, while this is negative as E is in opposite direction of P cap. Okay, yes. And now a bit of simple math. First we'll take common, and we have 1 by r minus a the whole square plus 1 by, actually not plus, 1 by r plus a the whole square P cap. The LCM and all of that, if we continue with that. So here it will be r plus a the whole square minus r minus a the whole square. This entire thing divided by r minus a whole square into r plus a the whole square. P cap. Now, when we solve the numerator, what happens? So we have 4 pi epsilon naught. So this will result in 4ra, while the denominator is in the form of a plus b into a minus b. So this will be a square minus b square the whole square. P cap. Right, guys? Again, I hope you guys understand how 4ra comes into picture. A plus b into a minus b, basically. Sorry, not a plus b. A plus b the whole square minus of a minus b the whole square. If you use that formula and solve, you'll end up with this. Right? So that's it. One last thing. Substituting, just a minute. Substituting moment, which is 2a times of r, not r, sorry, q. So we have q, and here from here we have 2a. So basically, this will turn out to be 2p r by 4 pi epsilon naught into 1 by r square minus a square the whole square p cap. Right? This is for a distance wherein r is greater than a, but not that great. What if we have r a lot greater than a, far away from a? What happens? R square minus a square will be approximately equal to r square, right? Therefore, your electrical field at point P will be equal to 2pr divided by 4 pi epsilon naught 1 by r to the power of 4. Agree? So this and this will get cancelled. So we have 2p by 4 pi epsilon naught 1 by r to the power of 3 p cap. So that is your scenario wherein r is a lot further from a. I mean, it's a lot bigger than a. So from this, what can we conclude? So this is the conclusion that we have made in one of the videos. For points where r is much greater than a, the electrical field strength reduces at a rate of 1 by r cube. Agree? Now, we are trying to understand what's happening over here. So what can we conclude over here? That the electrical field outside the dipole is pointing in the direction of the dipole moment. Right? You can see it over here also. This is the dipole. Within the space, we know what's happening. Outside the space, along the axial line, it will be in the direction of dipole moment. Can you see that here? Sorry, I think you guys can't see my mouse. So it is after red point, right? Red is your positive, blue is your negative. So just observe before and after the positive and the negative. Right? Observe this. Within the space, it's something else. but outside the space. So it's going towards negative, obviously, and next left of red, it's going away from negative. So it's in the direction of dipole moment. And that's what our derivation spoke of. So how do we do this? First, we need to write statements telling that we are considering a point P, which is r units away from the center, and we need to draw the diagram. And using our superposition theorem, we end up with the resultant electrical field at point P being equated to sum of these two. A bit of math, and we end up with this expression. And a point which is much greater than A, we end up with this result. So depending on what is asked, you guys can do this. So now it's time for you guys to pause and copy.